Okay, so and we're going to finish actually up the system dynamical part, and next week we're actually going to start controlling actual designing controllers. So what the whole lecture is about, right? So, but in this first part, we need to set the basis, so to say, for what we can do with our systems and analyze them. And in that regard, I've showed you last time the Laplace domain, right? So we introduced it and we figured, okay, there's this nice thing about the block diagram algebra, where we can actually not only make use of it, but there's actually a mathematical meaning behind it. So we can have signals, right, which are propagated through a system and lead to an output. And this is actually not just any arbitrary drawing what I like to do, but it's really also has a mathematical meaning, because we just can think of multiplication and addition of signals. And this is the big advantage we have in the Laplace domain, where we can use or we can apply basic mathematical operations like multiplication, division, addition to our systems, while in the time domain we would have an ODE, right? And there it's not possible to just like multiply systems together, because there are nested integrals in there. Okay, so today I actually wanted to kick off the lecture with another example of the block diagram algebra. Okay, so let's do block diagram algebra. So you just grab a piece of paper, because this doesn't go in the script, and you follow me. So what is the good thing here in the Laplace domain? The Laplace domain allows us to simply multiply a transfer function, right? Simply multiply transfer functions. And as well signals, right? So, right, remember, this is not possible in the time domain, because in the time domain we have integrals, we have differentiators there. So this cannot be done in the time domain. And you will often find systems, right, in books, just written down, or in papers. If you read scientific papers, they are just written down in actual little block diagrams instead of ODEs, or instead of transfer function, because it's so nicely. It's just a better illustration than the mathematical equations. And I want to do one example with you. And we have a system given, but not as a transfer function, not as an ODE, simply as block diagram. And I'm going to draw the block diagram for you, and then we want to get out the transfer function of this system, right? Okay, so the block diagram looks the following. We have a simple 1 over s there, which we learned last time. It's an integrator. We have a constant factor, which is a 3. And then we have a feedback loop, which is equal 5. And we have this, we have a summation here where we goes a minus. And we have another transfer function, which here is 0.1 over s plus 3, sorry. And what goes in here is our input u. And what goes out here, actually we have another path here, which is equal to, and this guy adds here at the end, and here we have the output. So, and this is your system, right? You have an integrator in there, you have some constants, you have a transfer function in there. And as engineers, what we are actually interested in is how is our output influenced by our input, right? So how our input influences our output. And we know that this ratio is simply given by our transfer function, right? So by this system here. Unfortunately, there is not a single system there. It's just a composition of a lot of small subsystems. And this is where I've shown you last time, where we introduced the block diagram algebra, how we can kind of reduce this again to a single transfer function, right? Remember, I've shown you this with a feedback loop for different signals. And you will see in this exercise I uploaded, there are a lot more examples you can do, but I just want to do one more together so you get a little bit of practice there. I've also shown you last time this calculation trick, right? So we're going to do both things. We're going to simply compute it plain and simple from the back, which is the first way, and I will show you also the calculation trick, so to say. So what you always should do first when such an example appears is look for feedback loops. And this is actually often a source of mistakes, so to say, that students actually don't realize the difference between a feedback loop when a signal is fed back, right? So this guy here runs back because the arrow shows to the left, while this guy is just a forward loop, right? So this is not a feedback loop because the signal always runs to forward. We are actually looking for dedicated feedback loops because this calculation tricks only works for feedback loops. Okay, so we got one feedback loop here, and the idea here really is to one strategy is, right, to kind of simplify this block diagram by decomposing the feedback loop first, because all the others stays the same. So it's sometimes really unhandy when you get a very big problem, right, that you go from the back to the front because the equation is going to be bigger and bigger. So really try to reduce your problem into subparts. When you have an isolated feedback loops, you can always do this, okay? So let's start out with this feedback loop. I'm just cutting this guy out here, right? Let's name this, you can always name a signal. We name this U tilde and Y tilde. So let's take a look at the feedback loop here. We have U tilde, and you will see when you get a little bit of practice, you will actually get much faster with that, but I'm now in the lecture doing it on the slow side so everybody can hopefully follow. Right, so we got this isolated feedback loop, we get our Y tilde here, and okay, so let's solve that simply from the back. So let's call that option 1, right? Option 1, we do it from the back. Okay. So, we start at Y bar, Y tilde. Okay, this goes 3 times 1 over S multiplied, and we got the summation here, right? This is always a good location for a bracket, right? Okay, so we got U tilde plus, minus 5 times, and we are back at Y tilde. Okay, so the good thing now, or this is the goal, that you always have only the input and the output there, right? Because now you can transform it and you without the transfer function. So if you bring that to the other side, you got Y tilde multiplied by 1 plus. So we multiply this guy in there. So we got actually 15 over S, and that's it, right? And on the other side, what remains is 3 times U tilde over S, if I'm not mistaken. Okay, now we divide through the bracket, and what we get here is 3 over S over, and we bring that on the same denominator, we got S plus 15 over S. And this is actually equal 3 over S plus 15 times the U tilde missing times U tilde, right? So we resolved this feedback loop, right? So really coming from the back and do it, do it from the back and with basic mathematical operations. So the second one was this calculation trick. where we said, okay, if there's a feedback loop and it's only holding for a feedback loop, that's important to remember. We can go, the transfer function gets, we're going to go direct from the input to the output, and we're going to 1 minus plus or plus minus, you need to change the sign here, the feedback loop. Okay, so let us do this for this guy here. We're going to change the color. No. If we go from U to Y directly, it is 3 over S, right? Okay. This is 3 over S. And we got 1, and now we have a minus here, so we need to go 1 plus. And we're going to go through the loop, which is 1 over S times 3 times 5, it's 15 over S. 15 over S. Okay, so we multiply together, and you already see it kind of looks like what we had here. We end up with 3 over S plus 15. So it's equal, right? So your G of S is, so I hope you can see that's the same. Okay, so let us take a look on a big view what we have achieved by now, right? So we do an update on our system here. So let's go up. What we did is we actually only resolved this guy here, right? So this what's in the cloud, so to say here. Okay, the rest we didn't touch yet. So let's do an update here. Okay, so we had our input U. This guy went through this system 0.1 over S plus 3. Then we had the summation loop, but this actually we have resolved by now. So our new system is actually, here we said it's U tilde, it's 3 over S plus 15. And here what goes out is this Y tilde. Okay, and then we're still having this summation here, right? So the forward pass, if you look here, this one here, and we have this forward pass with a 2 here. Okay, so we need to go from here to 2 and add this together at the end here. And this is our output Y, right? So you see it's already gotten a little bit simpler. So we don't have any feedback loop now, and actually forward loops are actually usually pretty easy to solve because you don't need to look for the same variable again, you just can go from the back to the front. Okay, so let's do this. If we would say now Y, this is what we are looking for, our output is nothing but 2 plus 3 over S plus 15, right? So we go here, it's 2, and we go here, it's 3 over S plus 15, and we reach U bar, so U tilde, right? So we don't stop there. We don't stop at U tilde, we just get U tilde away, and we go further to the front, and then we multiply by 0.1 over S plus 3, and now we are finally reaching our desired input U of S. Okay, and now it's just really simple, bringing on the same denominator and so on. So let's do this. So this guy here becomes, I'm going to do 2S plus 30 plus 3 over S plus 15, right? Multiplied by 0.1 over S plus 3 times U, and this is finally we leave out this S, or we leave the poles there, so to say. We're going to discuss today what poles are. You don't need to multiply this out. It's actually already in a very nice form, and we are left with 0.2S plus 3.3, right? So, and this guy now describes your system G of S. And remember, this is your system. It's how your input is transferred to your output Y, right? This guy here is our system. This is our system. And remember, it's a transfer function, so it's in the system. It's a system. It's a system in. It's a system. I'm just reading the question. That's why I got stuck. This is a system in the frequency domain or in the Laplace domain. This what stands behind is an ODE in the time domain, right? This is always important to note. As a summary, always first try to look for feedback loops. And then simply resolve y to u, right? So you start from the back and you go to the front. Okay, so much for that. So we have the question in chat. If I can compute if I can calculate the example number 5 from the exercises I uploaded, yes, I can. That's the answer. But actually I will not do it because to be honest, if I'm doing it now and everybody sees it, it's going to be a very it's basically bypassing your experience of really trying hard to solve it. So if you really have a question, I would suggest you come into my office hour, which is on Tuesday at 12:30. And we can discuss it there. So I would favor this because if I calculate it now on screen, everybody will have seen the result. And as usually in engineering, when you see the result, it is easy. And actually, it's not that hard, this one. So this is why I'm not going to do it live in the lecture, but you can come to the office hour and we're going to do it there. One tip though, try to split up the last summation and see this as two channels because you only have one input and at the end there's a summation of two channels. If you split that up and just consider, okay, this summation at the end, these are before this summation, there are basically two signals. Let's call it y1, y2. And if you calculate these two guys separately, then the example actually gets pretty easy because then you can do the trick with the direct through one plus the feedback loop. I guess if this does not help, I guess I can explain it to you in the office hour. So I really would favor this one to not take the opportunity for other students away to break their head on that, so to say. Okay. So really, please try to do this block diagram solving because there's always an example on that in the exam. So I have not given any, or I have not seen actually, not only on my case, I've seen a control exam where students didn't have to solve a block diagram. So this is really important stuff because as soon as you work in control, the first thing you will see are not ODEs, it's going to be block diagrams. And we will need that, especially then when we design controllers and see how controllers interact with our system. Okay, so let's actually bring up the interim result where we stopped last time, right? And make our way forward from there. So, where are we at this point? We said, okay, by going to the Laplace domain, complicated integral and differential function simply become rational function where we can apply our basic mathematical knowledge without solving any integrals. We've learned about signal tables, right? We can look up, so we don't actually need to do this transformation from the time to the Laplace domain because a lot of smart people have done that before and we can just look it up. And by the means of block diagrams, we can actually really do calculations and multiply systems and signals together. So, is this everything we need? Actually, this is just a good starting point, I'd say, because the next thing you should ask is, okay, let's say we have a system. We have a PD2 system as an ODE, right? As we have learned it in the first part of the lecture. So it's a y2 dot and so on, or I have an integral system, I have a differentiating system. So how actually do I get now to the transfer function, right? So do I always need to do a full transformation of this guy with the integral? The answer is obviously no. And you will see that we only need 1 or 2 slides to now reveal this secret, because it's so simple. We only need a single rule and some basic maths to actually make to take the ODE and get our transfer function out of it. It's actually really not that difficult. Okay, so what do we do when we have this transfer function, which we will cover in a second? Well, then it's the interesting part is, and this is what is actually the important stuff, we can analyze our system using that transfer function, right? So we can take a look at the transfer function, and we immediately will know, is the system stable or not? Has it to a step response? Does it have an initial value? What's the final value if I put in a step? Things like that. Things like I would need to solve the ODE in the time domain. We can actually compute pretty plain simple in the Laplace domain, and this is what we're going to do today. Okay, and obviously we need some practice. So let's talk about the strategy first. How do we get from the ODE to our transfer function? So what's the imminent step there? Obviously, you can always do a full Laplace transformation with solving the integral, but this is way too hard. Nobody wants to do that. This is why, as I promised, you only need a single rule. Okay, and let's start with a very general ODE, right? So this is an ODE as we have seen it. It's a linear one, right? It's time invariant, so no explicit dependence on t there. So this could be any function here you have learned in the first part of the lecture. PD1, PD2, IT2, differentiating system, whatever you like. And the only rule you need is the following. We said if we have a signal and we want to know, we want to differentiate that signal, right? So you basically want to compute f dot of t, right? Okay, so if you have f of t, you simply, in the time domain, you would know how to differentiate, right? Ableiten. Everybody knows this, hopefully. Okay, there's another way, right? We said, okay, we can bring our signal, we can take f and bring it into the Laplace domain, and we simply call that guy f of s then. Okay, so how do we bring the derivative of f of t into the Laplace domain? Well, we just transfer our f to f of s, and then we multiply by s, right? So we don't need to do a differentiation. We don't need to do eine Ableitung. We simply bring it to the Laplace domain and multiply by s. So this guy here, if you transfer that back into the time domain, is immediately f dot of t, right? So you could actually compute the derivative with actually doing the Ableitung by just doing the transformation twice, right? So I hope you can see this workaround here. And the same goes for the integration, right? But here, for this calculation of the transfer function, we only need this certain rule. Why? Well, so take a look at our transfer function here. At our, not transfer function yet, at our ODE here. We've got y, we've got y dot, we've got y2 dot, and so on. And we know if we take that y here, y of t, and transfer that in the Laplace domain, it's going to be y, and you can write it in capital letters or not. I'm just skipping that. It's going to be y of s. So if we transfer this guy, it's going to be y of s times s, because it's a derivative. If we transform this guy, it's going to be y of s times, well, we're going to do the derivation twice in the Laplace domain. It's simply s squared. Okay, same goes for u. If we want to have u of t transferred in the Laplace domain, it's going to be u of s times s. Okay? Okay, so let's do this, right? So you see, you only need to replace all the derivatives in your ODE by s with the power of the degree of the differentiation you have. So you replace u and y by u and y of s. You replace the first derivative of y and u by y of y times s and u times s. And you replace the second derivative with y of s times s squared and u of s times s squared, and so on, right? Okay. So far, so good. So this is, and note, this is already the ODE transferred in the Laplace domain. And we simply applied a simple rule we can look up at any mathematical formula, right? So we didn't do any transformation, although we have already the transformed version there, right? So we just applied this basic rule. Okay, and now we know that our g of s, our transfer function, right? We want to have a compact form of our system S transfer function is just y of s divided by u of s. Okay, so what you need to do is you exclude y here, exclude and exclude, and then you divide it through, right? And then you got your transfer function. So it's really excluding u and y and then dividing it to the other side, and what remains on the left hand side is then y over u, right? And on the right hand side this guy remains, and this is the definition of your system. So you brought your system from the ODE into a transfer function in basically 2 steps, right? By just applying one single rule. Okay, let me try to summarize this idea on a little bit more compact form. Let's formulate a recipe, right? Because I know that students, when they learn, always try to look like recipes or schemas which they can apply, and it always works. Okay, so as a starting point, you have your ODE, right? Second order, third order, whatever you like, you name it. And then you replace all point sizes, so to say, alle Punktgrößen, with y of s and u of s times the corresponding power of s, right? For example, if you have the first derivative, you replace it by y times s and by u times s. If you got the second derivative with the second power of s. Then you exclude y and u, and you resolve for y. You can divide it through u as well, but you actually don't need to, because the transfer function will always be or already be there. Okay, so this is the recipe. Now let's try to apply to our famous mass spring damper. So this is the second order ODE, right? So it's a second order linear ODE. So what we want to do is the following. We said, okay, if we want to bring y2 dot of t into the Laplace domain, it's simply going to be y of s, and it's the second derivative, so we need to put here s squared. This guy here is the first derivative, so we need to multiply it by s. And this guy here is no derivative, so it's simply y of s. On the other side, there are no derivatives, so it's u of s. Okay, so we exclude y. Then we have ms squared plus ds plus c is equal u of s. So now we're going to divide by u, and we're going to divide by bring that to the left-hand side and bring the bracket to the other side, and it's going to be ms squared plus d of s plus c. And this, per definition, now is your system, your transfer function in the Laplace domain. That's it, right? And this is an equivalent description to the time domain. All the information we have in the time domain, we now have in this rational function. However, we can now simply do multiplication and stuff with it. Okay. Let's say, okay, we're gonna add to our spring mass damper system an actuator and a sensor, right? So we have an actuator and we have a sensor. This guy here is the spring mass damper system here, right? So the thing is, if you would do that in the time domain, you should see that you will get 3 ODEs, because the actuator might have an ODE and the sensor might have an ODE. So if you want to solve that for an arbitrary input u of s, you will gonna have an 3 times nested convolutional integral, dreifaches Faltungsintegral, right? Because when we put in u, a step or something, then we can solve that. In the Laplace domain, we're going to simply multiply all these systems together. Okay, I will show you that. So let's assume we have PD1 systems for the actuator and the sensor. So both PT1. So you should realize that these are PD1 systems, right? So the actuator has as input the valve position or the current, and has as output the position of the rod U, right? So it's a PD1 system with a time constant and with a gain. So if you do the transformation, and let's call the transfer function G actuator, it's going to be the output, so U of S, over the input, U commanded of S. And if you apply the same scheme as above, you will see that it's going to be K actuator over T actuator times S, because we have a first derivative here, plus 1. Same goes for the sensor. Let's call this G sensor. What do we have as input? As input we have our Y, so the position here of the mass, right? We named that Y. So this is the input to the sensor, and the output is the measured position of our mass, right? So it's going to be sensor of, not of T, obviously, of S. And it's again a PD1 system, so it has to look like 1 over, because it doesn't have a gain here, 1 over T sensor times S plus 1. So we got 3 systems now, and they're all transfer function. And the question now is, as I always telling you, as engineers, we are often interested what goes in our system, what goes out. In this case, what goes in is a current into our evolved position on our actuator, and what goes out is the measured position of the sensor of our mass, right? Think of the espresso machine example. What goes in is the power into our heating element. What comes out is the temperature, or the measured temperature if you have a sensor. So instead of solving all these 3 ODEs, we're simply going to do this in the Laplace domain. So the idea here is, and now I'm coming back to block diagrams, what goes in is our commanded voltage, and what we get out is our sensor. So if you would take these 3 ODEs here, it's going to be pretty messy to get this relation. However, here it's a simple forward block diagram, right? And we simply go from the back to the front. We know the measured position is nothing but take the sensor, take this transfer function, multiplied by our system, and our system is G of S, right? The spring mass damper system, and finally we reach the actuator. And we reach the input, which is our input valve position, or current, whatever you like. And this guy here now, describes our system, right? And you can do now, obviously you can solve this and can do manipulations and multiplications and multiply this out. But this guy here describes your system, your overall system, which would include 3 ODEs as one rational function. And you can apply multiplication and stuff, whatever you like, right? Without actually thinking there's an integral function behind. We don't care. It's in the Laplace domain. We don't need integrals because we know an integral is just 1 over s, right? So I hope I could convey or convince you that doing mathematics or doing control in the Laplace domain is much simpler than in the time domain. Although I know it always takes a little bit of time to get this abstraction in your head. But really think of systems, just a different description, not as a function of time, but a function of s. And this s helps us to work with our systems. Okay, now you know how to transfer any transfer function or any ODE into a transfer function. And the last part of the system dynamics for today is what can we do with this, right? Because at this point, it doesn't look like, okay, we understand we can do easier computations, but how do I get information out of this transfer function, right? So this is the problem now, because if I want to know how my system, how my espresso machine reacts to 0.25 kilowatts, I can solve the ODE, I know that. But now I cannot solve it anymore because we are in the Laplace domain. And you will see in the Laplace domain, it's actually much simpler to compute these things because we don't need to solve the ODE. There are a couple of theorems we can apply and immediately know where our system is going to a certain input, right? And this is what we're going to do next. Okay, so now we have our transfer function and we want to make use of this transfer function to analyze our system. All right, so this is the idea. Okay, here's a short introduction which I just tried to tell you. Okay, what could be interesting when you think of a car or an aircraft, right? How does my system react to different input signals? How does it react to a step? How does it react to a ramp, a sine wave, an impulse, things like that, right? In the time domain, you always need to solve the ODE, not in the Laplace domain. Yeah, this could also be an interesting thing. How does the system react at the beginning of the input signal, right? So far, we always said, okay, we are mainly looking at the end, right? So we are exciting our system, something is happening, the eigenmotion, and then we're going to go to a steady state value. And we are in lab exercises, we mainly computed those steady state values, and said, okay, if we put in 0.25 degrees kilowatts, we get to 125 degrees. So we looked at this final step. But you could also say, maybe there is an initial reaction already, right? Or is there an initial reaction as soon as I apply my 0.25 kilowatts? Does my system do anything, or is it still zero at this point in time? So right at the beginning, this is called the initial value problem. Okay. And obviously, you have seen when we talked about the PD1, PD2 system, we were always also kind of interesting what's happening between this initial value and the final value. Is it oscillating, or is it just going aperiodic, right? So these are things we are interested in as engineers. And last but not least, is our system actually stable, right? Is it going to infinity, or is it going to the steady state value I just always talk about? Right? This is a matter of stability. Remember this my example with the stick. If I let it hang loose, it's actually going to a steady state value which is at zero. But if I hold it like this, it falls down, so it's not stable, right? So is there an actual steady state value, or is it going to infinity? Does it oscillate? Right? Things like that. In the time domain, to answer these questions, we need to solve it, especially for the first two, or at least we're going to need to solve the homogeneous solution, right? Or solve for the homogeneous solution, which were the computing these lambdas, if you remember, which were solving the characteristic equation. And you will see there's a direct link from the characteristic equation in the time domain to our transfer function in the Laplace domain. Things are pretty similar. Okay, so these are things we're interested in, and we're going to go through those things step by step. And we're going to actually start out with the first two of those. Okay. So, and the next thing is a little bit mathematical, but it's only one slide. So I'm not going to prove it. I'm not going to show you derivation. We are engineers, so I'm just giving you the result, and then we're going to apply it, right? So the idea is, and it's called the initial and final value theorem. So the theorem is actually a couple of pages long. We don't going to go through it. I'm just presenting you the result, and I'm giving you the big picture why we're going to do this now. So as I said, I give you a transfer function, and I give you an input. And you want to know what my system is doing. What steady state value do we get? And what's the initial value? And we want to know, we want to extract this information from our transfer function. And we can do this by applying the initial and final value theorem. And I'm showing you the theorem now. On the next slide, we're going to actually apply it. Okay, so under certain conditions, and the condition is pretty simple, the condition is that the limit value needs to exist. We can determine directly the value of the original function at t equals 0, which would be the initial value, and for t going to infinity, which would be the final value, from the transfer function. And remember, we have two things here. We have two things here. We are talking about the time domain. We are talking about what our system is doing over time. But we have a system which is dependent on S, right? And there's no t in our transfer function. But the final and initial value theorem connects time and Laplace domain. So this is the big picture here, right? So the initial value theorem just says, okay, let's assume we have an f of t, which is any function in time, right? And we want to know what is this function doing when we let t go to 0. So we need to do a limes and let t go to 0. You can just put in 0, right? But mathematically correct if you let t go to 0. In the Laplace domain, this would simply be take your Laplace transformed f of t, multiplied by s, and this s here is important because it's often forgotten, and then let s go to infinity. And that's it. So this is really a strong argument, right? Because we, as engineers, we are like the time domain. Yes, I agree with that. And we want to know what's our system doing when we just start our process, when we start our car, when we put in a step into our car, right? So at t equals 0, what's happening? But we only have the transfer function now because we don't want to solve the ODE. Okay, we take the transfer function, we multiply it by s, and then we're going to let s go to infinity. And what the result of that process is actually our initial value in the time domain without any transferring back and forth, right? Okay, so now you could say, okay, we have f of t here, right? What's f of t? Well, now I'm going to try that connect to our system, because in the Laplace domain, we said our system is y of s is equal our transfer function by multiplied by u of s, right? So what does that help us? what if we have a system? If we have a system instead of f of t. Well, our system is simply y of s equal g of s. Our system output, sorry, is simply y of s, taking your transfer function, your hidden ODE, so to say, and multiply it with the input. And what you are interested in is what is y of s doing at the beginning. So what you ultimately want to know is what is y doing at the beginning, right? So, okay, you just plug in y here. T going to 0 and s going to infinity, and you have your y of s times s. Okay. We have not done very much yet, right? We just said, okay, we don't have f of t or something. We have an output of our system. Well, this is kind of problematic now because we don't know our y of s, right? We don't know the output. So how we cannot plug it into this final value theorem because we don't know it. Well, we don't know it, but we know its relation, right? We know that y of s is simply this guy here, and we know this one, we know the transfer function, and we know our input. Okay, so let's plug that in. G of s times u of s times s. And then we let s go to infinity. And now we have everything to apply this theorem to a system, right? Because we know the system and we know the input. And then we can compute the initial value, right? So this would be coming from the very general mathematical description, how you find it in books, to our actual system problem, right? Instead of f of s, you need to put in your system times the input. And now you already see you can put in any input there what you want. You can put in u of s being a step, an impulse, a sine wave. You only need to solve this guy and you know what the initial value is going to be without solving the ODE. And this is actually pretty cool. So you will see now I've talked about the initial value. There's also a final value theorem. And to be honest, the final value is usually the more interesting one for us as engineers because we want to know what's happening if we wait long enough, right? Okay. But it's not much of a difference. So the final value theorem, we have a function f of t, and we want to know what's happening if we just wait long enough and let t approach infinity, right? In practice, it's not going to be infinity, it's going to be a long time. Okay, in the time domain, in the Laplace domain, this transfers over to f of s times s. It looks the same. The only difference is here you need let s go to 0. So really, the difference lies not in the limitation value computation. The only difference what you have is here, right? So this is what's changing. The same what holds here also holds here, right? If you want to now relate this to a system, just plug in g of s times u of s. Okay? Okay, so I know this is kind of, well, you will see, you will figure out this is kind of the basic math, but we're going to do actually a couple of examples now and to just get some practice in. And as usual, we're going to start with our famous spring mass damper system. Okay, so we have our spring mass damper. We have an input u, and we are interested in the position of our mass takes at the output. You should realize by now that the transfer function of this system is g of s. G of s looks like this, right? It's 1 over m s squared plus the damping times s plus c. Okay? So now we have to define our input. And we said, okay, at this point in time, we're going to look at a step input. So we're going to apply a step input to u of t. So u of t is sigma of t. Now, question to you, what do we do next? Well, what we're going to do next, we have g of s, but we need u of s. Question to you for the chat, because I need to drink something. What's u of s now if we have a unit step? You can write here unit step. How does u of s look like? So if you, yes, 1 over s, right? So this is simply 1 over s. Okay, now we've got everything together to compute our output y of s, because our output y of s is simply taking our system and multiplied, sorry, not plus c, and multiplied with the input, and the input is 1 over s. So this is our output in the Laplace domain. Okay, now we want to know where is our system heading to when we just wait long enough. So final value theorem means what happens for t going to infinity, right? Okay, and you remember from the last slide, or I'm telling you, that if you let t go to infinity of your y of s, and y of s now is simply, let's write y of s, it's shorter, not y of s, y of t, we need to let s go to 0 of our y of s and multiply it by s, right? Don't forget this s here. Okay, now we plug simply in what we have. Okay, we get s going to 0 of 1 over ms squared plus d times s plus c times s, and the input is 1 over s. Well, immediately cancel this guy. Now we let s go to 0, right? Change the color so that it's visible. So if s goes to 0, this guy gets out, and what remains is 1 over c. And this kind of makes sense now. Think from a mechanical perspective, right? If I make my spring constant harder, stronger, so if I increase the spring constant for a certain input, I will not reach that far. So it needs to go inverse, right? So for large spring constants, my displacement of the mass will be lower. If I have a very low spring constant, I can push with the same force my mass further away. This is what you see here, okay? So you know now what happens when you put in an input, a unit step to our function. And remember, we did not solve any ODE, right? We just did some basic calculations. Okay, now we could also say maybe we are also interested what happens at t equals 0, right? So what happens if, change the color, what happens if we let t go to 0 in our y of t? Well, this transfers over to s going to infinity times of s times y of s, which is simply s going to infinity of, again, we have s over s here, that doesn't change. Then we have 1 over ms squared plus ds plus c, right? So here it's a little bit problematic. What happens when s goes to infinity here? It's technically you could immediately say if this guy goes to infinity by infinity squared, this goes to infinity, this guy gets pretty large, so it needs to get to 0. Yes, that's true, but it's not fully mathematically correct, because you cannot square, you should not multiply something m by infinity, right? So what you instead do is you divide by the highest degree of s, okay? It's just a mathematical trick here. So the highest power of s here is s squared. So we divide our whole system by 1 over s squared times 1 over s squared, right? So this is equal 1, so we allowed to do this, times 1 over ms squared plus ds plus c. And what remains here is 1 over s squared over m times 1 plus d times 1 over s plus c over s squared. So, and if you now let s go to infinity, this guy gets 0, this guy gets 0, this guy gets 0, and you are left with 0 over m, and this is obviously 0, right? So, but I agree if anybody of you says it's already visible in here, because if I divide 1 by some large number, it's, mathematically it's not correct, because you have infinity squared plus infinity. So what's that? This is not actually really defined, right? From a practical point of view, you could say it's again infinity, but mathematically you are not allowed to. So this would be the clean way, but yeah, I leave it to you how you do it, right? Okay, that's it for that. So how do we continue? Yeah, let's keep on going with 2 more slides, and then I have some examples to calculate on, and So from this initial and final value theorem, we can actually derive some really nice interpretations here. Let's say we have an arbitrary transfer function like this guy here, right? And you should realize this is exactly the same thing as we had when we introduced this calculation scheme of the transfer function, right? So what you can say here is, if I apply the final value theorem, I let all these s's go to 0, right? And what remains is just this b0 over a0. So I hope you agree with me. If you apply this guy here for a step input, this will all go to 0, and you are left with this one, in case you have a step input, right? And this b0 over a0 has a distinct definition. This is called the static gain of a system, and it's equal to the final value of the step response, right? So it's just a definition we like to use in control, because it's so helpful to have a dedicated variable in our transfer function. This is simply our static gain. Why is this important? Well, on the one hand, the static gain if I tell you I have a system with a static gain of 5, you immediately know if I put in a unit step, it goes to 5 if it's stable, right? But we will see later on in 1 or 2 months, the static gain also tells you how is a sine wave transferred to the output, how is the amplitude changed with very low frequency, with a frequency of approaching 0. But leave that aside for now. The static gain tells you immediately the answer to your unit step response, and this is why it's getting a dedicated name, the static gain. Okay. So if you know the static gain, you immediately know your system's response to a transfer function. And you don't need to even apply the final value theorem, because you just look at the constant values where no s's appear, and you immediately know your static gain, right? So if I give you a transfer function, 1 over s plus 1 has a static gain of 1, the transfer function, the final value of a step input, of a unit step input is 1, right? If this was too fast, if I give you a transfer function with 0.5 over s plus 1, look at the constant terms, 0.5 over 1. This is your static gain, 0.5. So your system answers to a unit step with 0.5, right? So this is really powerful because you just need to visualize your transfer function. You immediately know what's happening. Okay, so this explanation is in the line below. So if we look at the lowest terms of S, we can also look at the highest terms of S, right? So these what are written here in red, and this is the so-called initial value of the step response, right? See, the blue ones are the final value immediately to a unit step, and the red ones are the initial value. So, but now you could say, what happens if I don't have s squared and an s squared in the denominator and in the numerator? Well, if m is smaller than n, you always have an initial value of 0. So this holds, for example, for PD1, PD2, and so on, right? Only if you have the same degree here, like let's say you have a system which is s plus 1 over s plus 2. This guy has the same degree, then you have something, you have bm equal 1 and an equal 1. Then you have actually an initial value. If you don't have the same order, you immediately know that your initial value needs to be 0. And this is always true, right? Even for unstable systems, let's just decide. So I give you a transfer function, you take a look, and you look at the highest orders of S, and you immediately know your initial value to a step. And this is actually pretty cool, right? So you could say now, what if in the below the line there's a higher order above in the numerator? What's happening then? Well, this is not possible for physical systems because remember, we said when we introduced the differentiating system, right? A differentiating system would simply be 5s. We said this is not possible, it's not causal. So we can conclude for the transfer function always needs to hold m is smaller than n, because if n is bigger than m, it's not a physical system, and it doesn't exist, so to say. It's not causal, and there are no not causal system in nature, because we would have to see in the future, which is unfortunately not possible, let's say it that way, right? If m is equal n, this is called what we call a direct feed-through. Why is this called direct feed-through? In German, it's called direkter Durchgriff. That means your input directly influences the output when it's appearing. And this is, again, rarely possible in nature. Because remember, when you sit in your car, you fully hit the throttle, it's not going immediately, right? It will not immediately have a velocity, it builds up, right? So there's always delay in nature, and usually we have m smaller than n. However, we like programming filters and so on, and if we program filters, we actually can have m equal n, but n can never be larger than m, because that would mean we need to look into the future, and this is not possible, right? Bottom line here is really the takeaway for you should be, look at the highest degree and you immediately know, look at the parameters before the highest degree and you immediately know your initial value of your system to a step response. Well, please always refer to a step response, right? Why does it not hold for an impulse response or a sine wave? Because then your u of s does not cancel with the s, right, of the final and initial value theorem anymore. So be careful there. Okay, that's it for the theory in that part, and now I have 3 examples left, and we're gonna go back to OneNote. You grab a piece of paper, and we use the last 15 minutes to do a little bit of calculations, applying the initial and final value theorem a little bit to different function, and actually also directly practice a little bit this step coming from the ODE to your transfer function. If we don't get all the 3 done by now, we're going to simply start with them in the second part of the lecture. Okay. Oh, here we are. Okay, let me write down the initial and final values theorem one more time, that we also have it here, right? So that we don't need to switch over to the PowerPoint. So just for recapture, if we want to know how f of t goes is when we let time go to 0 in the Laplace domain, we simply let our Laplace variable go to infinity. We take f of s multiplied by s, right? And if we want to apply this to a system, this f of s is simply our g of s times our u of s, and don't forget ds. The final value then looks pretty similar. Let's try to grab this guy here and just do copy and paste. Oh, this was not supposed to be there. Okay, and the only thing which is different is now this here, right? So this is really the only difference. So it's not that hard to remember. For the final value, we want to go the time. We want to know what's happening if we just wait long enough, and that means we need to let s go to 0, right? Okay. Nope, this is not the right one. Okay. Okay, just leave it there. Okay, and example number 1. I give you an ODE, and the ODE is the following. It's 7 times the third derivative of t plus 2 times the first derivative of t plus 4 y of t, not the derivative of t, the derivative of y of t, and this is equal 14 times the second derivative of our input plus 2 times the input itself. And we're gonna define u of t is gonna be a step input, and actually we can do a unit step just for the sake of simplicity. Step input. Okay, and what do we want to know? We want to know the transfer function. Just for fun, we can also, what behavior does the system have? Right, so remember, is it the PD1 or what is it? And then we want to know the initial value and the final value to the unit step. So question to you, what system do we have here? Right, so try to answer that first. What system? Is it a PD1 or, yeah, what is it? Anybody has an idea what this system could be? Is it a proportional system? It's an integrating system? Does it have lag? What's the order of the lag? As I said, or as I explained last time, if you want to know the order of the lag, you need to look at the highest derivative of y, right? And if it's proportional, differentiating, or integrating, this is revealed by the right-hand side of the equation. Okay, so we have on the right-hand side, we've got a proportional part because there's no derivative. PD2T3, perfect. Thank you. PD2T3. Yes, that's correct. Because we have a proportional part, we have a second derivative, PD2T, PD2T3. So I think we are converging to PD2T3. Yeah. If you have just PD2T, this you miss the degree of T, but that's okay, I guess. At this point, it's probably a typo. Yeah. We've got the second derivative, so it needs to be D2, and we have this second order, third order of derivative for y, so it's a third order leg. Perfect. Okay. The transfer function. Okay, I'm going to do the transfer function, g of s. Okay, and the transfer function is simply 14s squared, right, plus 2, and the left-hand side with the y's always goes below, and it's going to be 7 times s to the power of 3 plus 2 times the power of s, 2 times s with the power of 1, so we don't need to write that, and 4. Okay, and now we're going to try to compute the initial value and the final value. The initial value is, let s go to infinity, and g of s times s over s, right? That cancels. Or you simply look at the highest. You look at the highest derivatives. Remember, we're going to look at here. We look at m and n. Let's see what m and n is here. M and n. So m is the upper part. So we've got 2. N is 3. So if m is smaller than n, it's always going to be 0, right? So m smaller than n, the initial value should be 0. And indeed, if we let s go to infinity here, again do the division, this turns out to be 0. Okay, the final value now, we let s go to 0 of g of s. The input is the step. This s comes from the final value theorem, and we just need to look at this guy here, and it's 1 over 2. Okay. Just for the sake of practice, let's assume we have what is the final value to a step input, and this time it's not going to be a unit step, it's going to be a step input which looks like the following. It's going to be, let's say, 32 times our unit step. Okay, what's the final value? And then we're going to finish the lecture. Does anybody have an idea? I mean, you could solve the ODE, right? But please don't. So by just looking at the final value theorem. And it should be actually pretty fast. Right, this u of t looks the following, a unit step looks the following in the diagram. Goes to 1, and this guy here then goes to 32. Yes, correct, right? So you don't need to do the computation because you already know how a unit step is transferred, and this guy just is 32 times higher. So your final value for your input u of t equal 32 times the unit step must be 1 over 2 times 32 is equal 16, right? Yes, perfect. Okay, so I think I leave it by that. I give you, there are 2 more examples, and we're going to do that in the afternoon. And I write it down, and you can do it during your lunch break. If you like, if you don't like, it's also fine. We're going to do it together. The first example is you have the ODE, second derivative of the output plus the first one is equal u of the first derivative of the input plus 2u of t. And what I want to know is behavior, the transfer function, and the initial value and the final value. Please take care when computing the final value, because we said there's a distinct restriction when we are allowed to compute the final value. So this here is a little bit tricky. And example number 3 is the following. I give you the transfer function immediately, 0.5 s over 0.1 s plus 1. And I want to know the behavior of that system. Oh, here I forgot the 2, what do I have here? To a unit step input. And here we have initial value and final value. Sorry. Short final value to a ramp. So it's different now. Ramp input, and the input is u of t is equal to times t, right? So it's a ramp. It goes up like this with an inclination here of 2. Yeah, that's it. So take the chance to practice a little bit, and I'm going to reveal the results, or we're going to go through these examples in the afternoon, and then we probably, I'm not sure if we get to the end today, but then we're going to continue with the analysis of our system using the transfer functions. Okay? Just give you 1 more second to, or you to just do a screenshot. I guess that's faster than writing it down. Okay, that's it. Main thing we did was today a little bit of block diagrams, but really the main thing was initial and final value theorems. Really look into that, because these are important tools basically, because it makes our life much easier, because we can directly analyze the transfer function and immediately know what the system is doing without solving any ODEs, right? Just applying this basic stuff. Talk later.